In example 9, you are given the graph of a one-to-one function. Okay, so everything is going to pass the horizontal line test and the vertical line test for that matter. So you're given the graph of a one-to-one function, and you need to draw in the graph of the inverse function. Okay, so you've got actually two graphs here. Okay, like I said, both functions both pass the horizontal line test, so they are one-to-one. So that means they'll have an inverse. So let's look at part A and try to draw in the inverse for this guy. Notice that you are not given an equation. All you have to go on is the graph itself, okay? And this graph has 4 points that are emphasized, okay? And so remember, all you need to do to get an inverse function is to switch x and y, okay? So that's what we're going to do. And you don't have to do this, but I'm just going to write it out for people. I'm going to make a little table with the old points and the new points, okay? So, all right, I don't know what I was doing here, but let's say this is old and this is new, okay? So, let's see here. Let's just go 1 point at a time. I'm going to go from left to right so that I don't miss anything, okay? So, the first point I'm starting with is -2, -2, okay? If you switch x and y, well, you get the same point, okay? So that point isn't going to move, okay? All right, the next point is 0, -1, okay? We're going to switch x and y. So the new point on the inverse function is going to be -1, 0, okay? Now let's go to 1, 0 on the original. Switch 0, 1 will be on the inverse. And then finally, 2, 1/2, which is the same thing as 0.5. Do your switch. The point on the inverse function will be 1/2, 2. Okay, so again, these are points on the original. These are going to be the points on the inverse. So all we need to do is plot these points and then connect them with the same shape. Okay, so this guy is going to stay the same. Okay, let's see. Then we're going to get -1, 0. Be careful on this one. The scale's a little tricky. The tick marks are going by 1/2 units. So it's like 0.5, 1, 1.5, 2, and so on. Be careful with that. All right, then we've got 0, 1. So that's going to be right here. And then finally, we're going to have 1/2, 2. So 1/2 is actually going to be right here, because remember, this is 1/2 and this is 1. So 1/2, 2 is going to be this point right here. Okay, so now we're going to connect with the same basic shape. So basically, you're drawing between each pair of points, you're connecting them with a line. Okay, so you're going to have this, this, and this. Okay, notice that they were generous enough to give you the line y equals x. Okay, whatever you graph. Okay, so let me label this. This is f inverse. This is f. Okay, your original function and your inverse function, they should be reflections of each other over this line y equals x. Okay, and you can see that if you folded your sheet of paper along this red dotted line, the two graphs would lie on top of each other. Okay, make sure, because I've seen some people do this in the past, make sure you do not confuse this with symmetry, drawing an x-axis symmetry or y-axis symmetry or origin symmetry. This is a different ball game, okay? If you're graphing in an inverse function, you are simply switching x and y and then plotting those coordinates, okay? It is not x-axis symmetry, not y-axis symmetry, not origin symmetry. Do not confuse the two. All right, let's try it on this next one, okay? So you have another graph, but this one's a little tougher because you don't get any specific points called out, okay? So you're going to have to kind of try it on your own, okay? First thing I would do is try to see if there's any point on the original function that lands perfectly on a grid point, okay? I see this point right here is 1, 1. The function appears to go through the origin, and it appears to go through -1, -1. Okay, so those are 3 points that it appears to go through. The problem is if you switch x and y on all 3 of those points, you're just going to get the same point back. So what that tells us is that the inverse goes through those 3 points as well. Okay, so everything else doesn't really land nicely on a grid point. So you're going to have to just kind of eyeball this one and use the fact that the original function and the inverse function are going to be symmetric about this line y equals x. So this red dotted line will help you here, okay? You know that if you fold your sheet of paper along the red dotted line, the original and the inverse should lie on top of each other. Okay, so I'm going to kind of do this one in segments, okay? Let's start with this little square right here, okay? Imagine folding this guy over the red line, okay? You're going to get something that looks like this, okay? Almost a leaf, okay? That's not perfect, but it's the best I can do here. If you folded your sheet of paper, the blue, or sorry, this segment should lie on top of this segment, okay? Let's focus in on this little square right now. Same thing, fold the sheet of paper. Where is this guy going to go? It's going to look something like this. These both look like leaves to me, okay? And then we can concentrate on this little square over here, okay? Fold the sheet of paper along the red dotted line. Where does this go? Okay, it's going to do something like this, okay? And then lastly, let's look at this square. Fold the sheet of paper along the red dotted line. Where does this piece go? Okay, it's going to do something like this, okay? And so this is going to be your inverse function, okay? We don't really know any specific points besides 1, 1, 0, 0, -1, -1, okay? Those 3 points go through both the original and the inverse, okay? You had to really heavily rely on the symmetry about the line y equals x to do this particular one, okay? All right, last example in this section is going to be example 10, okay? And this has to do with the last fact that we discussed, facts about an inverse function and the original function. And let me see if I can pull that up so we can reread it, okay? The sixth property said that if you are dealing with a function and its inverse, okay, if you compose them in either direction, so if I do f inverse composed with f, and I do f composed with f inverse, so I'm doing the composition in both directions, I will get the same thing, specifically x. And this is a way to verify that two functions are inverses, okay? All right, so in example 10, you are asked to verify that the given functions f and g are inverses of each other by showing that if you do both compositions, so you do f composed with g and you do g composed with f, you're going to get x in both cases. That proves that they are inverses of each other, okay? All right, so let's do it. You just have to do the composition in both directions and you should get x, and that proves that they are inverses, okay? So I'm going to start first with f composed with g. Okay, so remember, in this case, you are plugging g into f. Okay, so I'm going to go to f, go ahead and write it down. Go to f, because that's what I'm plugging into. Everywhere I see an x, I'm going to replace it with g, which is x plus 4 over 5. Okay, so I'm going to get 5 times x plus 4 over 5 minus 4, okay? And then I need to simplify this, okay? All right, so remember, this is 5 over 1 times the fraction x plus 4 over 5, okay, minus 4. All right, so to multiply fractions, you need to multiply across the top and across the bottom. So you're going to get 5 times all of x plus 4 divided by 5 minus 4. And then you have 5 divided by 5 is 1, so those guys cancel. And it leaves you with x plus 4. But don't forget the minus 4. And then the 4's cancel and leaves you with x. Okay, so that direction is good. You did the composition in that direction and you got x. All right. It is not good enough to verify just one direction. You need to make sure, because we've seen in the past that if you do composition in both directions, you don't necessarily get the same thing. So you do need to check the other direction to make sure you get x as well. Okay, so now we're going to do g of f of x. So this time we are plugging f into g. Okay, so I'm going to go to g because that's what I'm plugging into. Everywhere I see an x, I'm going to replace it with f, which is 5x minus 4. Okay, so I'm going to get 5x minus 4. Okay, so that's this replacement. And then I have the plus 4. Okay, everything is divided by 5. Okay, I'm going to simplify in the numerator. The 4's cancel. Okay, so I'm going to get 5x. There's still a 5 in the denominator. And now 5 divided by 5 is 1, so I'm going to be left with x. And so this works. Okay, this verifies by doing both compositions, okay, and getting the same thing, namely x. This verifies that these functions are inverses of each other. Okay, so I just want to say a little bit about something else about this. Another way you can verify that two functions are inverses is simply by taking one of the functions and finding its inverse. So if I had taken this function and gone through the process of making f of x, y, and then switching x and y and solving for y and getting the inverse, checking to see if this is the function that I get. Inverses are unique. So if this guy has an inverse, which is this, the only function in the world that it could be is this function. There is no other function that can be an inverse. Okay, so there's actually two ways you can verify that functions are inverses of each other. One is to do what we just did. You do the composition in both directions. Make sure you get x both times. Okay, the other way is to just take one of the functions, find its inverse, and see if you get the other. That's another way to check if they are inverses. And that's the end of this section.